Welcome to this lecture on homogeneous wave equations. Today we are going to explore the fascinating mathematics behind how waves travel through space and time. Whether it is a ripple on a pond, the sound of a guitar string, or a seismic tremor traveling through the earth, the principles we will uncover today govern them all. Let us dive in and build our understanding from the ground up. Now that we know what we are studying, let us visualize it. Imagine you are holding one end of a long, tight rope and you suddenly flick your wrist up and down. You will see a bump travel down the length of the rope. Once you flick your wrist, you do not need to keep touching the bump to make it move. It travels entirely on its own momentum. In mathematics, we call this self-sustaining travel a homogeneous process. This simply means there is no outside force pushing the wave after that initial moment. The wave equation we will study connects how the wave accelerates over time to how sharply it curves in space. This physical intuition leads us directly to the mathematical rule. The homogeneous wave equation is a partial differential equation written as u double t equals c squared times u double x. Conceptually, this relates the second derivative of displacement with respect to time, which is the wave's acceleration, to the second derivative with respect to position, which measures the wave's curvature. The constant c represents the speed at which the wave travels. Therefore, c squared is the wave speed squared. If the constant c increases, the wave travels faster. Physically, this means a stiffer string or a lighter material will cause the wave to zip across the medium much more rapidly. With our formula established, we need a way to solve it. To find a general solution to this complex equation, we use a clever mathematical trick called a change of variables. Instead of looking at the wave from a stationary point on the ground, we imagine running alongside the wave. We define two new moving coordinates that travel along with the wave's natural speed. The variable xi represents a coordinate frame moving to the left, while eta represents a coordinate frame moving to the right. By switching our perspective to these moving frames of reference, the complex math simplifies beautifully, allowing us to unlock the behavior of the wave. Now that we have our moving coordinates, let us see how they transform the equation. By applying the chain rule from calculus to our original derivatives, the wave equation transforms into an incredibly simple form. The mixed second partial derivative of u with respect to xi and eta equals 0. This means the rate of change in the left moving direction does not depend on the right moving direction. Next, we integrate this equation with respect to eta. Because the derivative with respect to eta was 0, eta acts like a constant during this step. The result is a function that only depends on xi, which we call arbitrary function f of xi. Continuing from our first integration, we now integrate a second time. This time, we integrate with respect to psi. This gives us our general solution in terms of the moving coordinates, yielding capital F of psi plus capital G of eta. Here, capital F comes from integrating our previous function, lowercase f, and capital G is the new constant of integration depending only on eta. Finally, we substitute our original variables back in. This gives the final result, known as D'Alembert's solution. It tells us that any wave can be broken down into two separate sheets, one traveling left and one traveling right. Let us visualize what this mathematical solution actually looks like in reality. The diagram you are seeing perfectly illustrates D'Alembert's solution in action. On the vertical axis, we have the displacement of the string, and on the horizontal axis, the position. At the top, at time t equals 0, we see a single initial disturbance. As time progresses to the middle and bottom stages, the energy naturally divides itself equally. Half of the wave, labeled f, travels to the left, and the other half, labeled g, travels to the right. This splitting behavior is the fundamental characteristic of all homogeneous wave equations. Now that we understand the general behavior, we can look at the specific formula used when we know the starting conditions. This is the full D'Alembert formula for an initial value problem. also known as the Cauchy problem. Conceptually, it combines the effects of the string's initial shape and its initial movement. The function f represents the initial displacement, or the starting shape of the wave. The function g represents the initial velocity, meaning how fast the string is moving at the very start. The variable s is simply a dummy variable used temporarily for the integration process. If the initial velocity increases, the contribution from the integral term becomes larger, creating a larger overall displacement. Let us apply this formula to a concrete situation. Suppose we have an infinitely long string. At time t equals 0, we pluck it, so its initial shape is given by a sine wave. We release it from rest, meaning its initial velocity is exactly 0 everywhere. We need to find the equation for the wave's position at any future time. Because the string is released from rest, the initial velocity function g is 0. This means we will choose D'Alembert's formula, and we can expect the entire integral term on the right side to vanish completely, making our calculation much easier. Continuing with our calculation, we see the integral term drops out entirely. This leaves us with only the displacement terms. We now just need to substitute our specific starting shape into the remaining formula. We replace the generic function f with our specific initial shape, which is the sine function. This gives us our final answer. Physically, this result means that the initial sine wave splits into two identical sine waves, each half as tall as the original, traveling in opposite directions at the wave speed c. Let us look at a different scenario. Now imagine a piano string that is perfectly flat at time 0, so its initial displacement is 0. However, a hammer strikes it, giving it an initial velocity of cosine of x. We want to find the displacement of the string at any time after the hammer strikes. We again choose the full D'Alembert formula. This time, the initial displacement is 0, but the initial velocity is not. The first part of the formula will be 0 because the string starts perfectly flat, leaving us to focus entirely on the integral part. Picking up from our setup, we plug the cosine function into the integral part of the formula, replacing the generic velocity function g. We must now integrate this initial velocity function over the interval defined by the moving wave boundaries. To solve the integral, we find the antiderivative of the cosine function, which is the sine function. We place the sine function in brackets to indicate that we must now evaluate it at the upper and lower limits of our integral, which represent the furthest points the wave's influence has reached. For our final steps, we substitute the upper limit into the sine function and subtract the result of substituting the lower limit. This yields our final answer. Physically, this final result shows that an initial velocity also creates two traveling waves. However, because of the subtraction in the formula, these waves interact differently than in our first example. Instead of just splitting, they create a growing displacement over time as the waves separate from the point of the hammer strike. We have covered a lot of ground today, so let us review the most important ideas. First, the homogeneous wave equation describes how disturbances travel through a medium without any ongoing external push. Second, by using D'Alembert's solution, we proved that any initial disturbance naturally splits into two separate waves traveling in opposite directions. Finally, we saw how the initial value formula allows us to predict the exact position of the wave by combining its starting shape and starting velocity. You have now mastered the fundamental backbone of wave mechanics, a concept crucial for everything from designing concert halls to understanding earthquakes. Great job!